Hi students, welcome back under the subject Algebra Number Theory in Unit 2, Finite Fields and Polynomials. Our topic for discussion is Irreducible and Reducible Polynomials. So part 1. So before getting on to the irreducible and reducible polynomials, this is my 5th lecture. So first 4 lectures, I guess if you would have followed, the first lecture was what is a polynomial and how to find the degree of the polynomial. Second lecture was how to find the root of the polynomial. Okay, what is the root of a polynomial? And in the first and the second lecture, you would have identified what is a constant polynomial, what is a zero polynomial, what is a leading coefficient. So what is leading coefficient? Do you remember what is leading coefficient? So when I say the degree of the polynomial is 5, which means that the highest degree term, that is x power 5, is present there. So what is the coefficient of x power 5? So first I will look into the highest degree term. So there I'll see what is the coefficient of the highest degree term. The highest degree term coefficient, if it is 1, then I call that particular polynomial as your leading coefficient. That is called as your leading coefficient. Okay. So that is the leading coefficient. As I told you, please brush up over the previous slides so that you will have a continuity in your studying process. And next third video was talking about division algorithm. So division algorithm was introduced by the famous mathematician Euclid, right? So do you remember the division algorithm? 2 lectures we had studied division algorithm. So it is going to be the dividend is equal to the product of the divisor into the quotient plus the remainder. So this is what the process was. You already know how to divide a polynomial by the another polynomial that you would have named as algebraic division. But here we name it as some division algorithm, right? And division algorithm in the sense we do it perform it under modulo. So whenever we see the coefficient greater than the particular modulo given in the problem, we got to divide and we got to reduce it to the remainder of that. So if we have a remainder, we substitute the remainder over there. If there is no remainder, that is we are getting it as 0, then we'll take out that particular, delete that particular term over there. So this is what we had studied in your 4 lectures. So moving on to the next topic, which is so important, called as irreducible and reducible polynomials. So what is this called as irreducible and reducible polynomials? So let's get into the PPT. So let's have the outline of this particular topic. So we start with basic definitions and then we declare some few problems with solutions, and problems for practice will be given later. And now what is irreducible and reducible polynomials? So a polynomial which can be factored, a polynomial which cannot be factored. So what do you mean by cannot be factored? You know what is a factor? In my previous lecture I had informed you what is a factor. So when an element is satisfying that particular polynomial, that will be called as a root. So that root can be written as a factor. For example, if I say 5 is a root, I can say x minus 5 is a factor. So a polynomial which cannot be factored into product of 2 polynomials. This is very, very important. So a polynomial which cannot be written as a product of 2 other polynomials with lower degree. It is called as a irreducible polynomial. Suppose if I can write it as a product of 2 polynomials, then I can call it as a reducible polynomial. That is the difference between reducible and irreducible. So basically by looking at this definition, few may not understand. So I had brought in a numerical example over here. The numerical example says, just look at the numerical example. X power 7 minus 5x square plus 7, right? So irreducible polynomials are also called as prime polynomials. The other name for irreducible will be called as prime polynomials. This has to be highlighted. So make sure you remember, at times if I'm going to use prime polynomials and irreducible are the same. Why this name? Just question yourself why the name given here is prime, right? What are the prime numbers? Can you tell me what is a prime number? Prime number is nothing but you cannot divide the prime number. The factors of prime number or the divisors of prime number are only the number by itself or 1. So now if I'm going to consider x power 7, what is the power of 7? What is the power of the variable 7? How can I write this as a product of two brackets? Can you please try? Can you take a paper and a pen and can you try this example to write it as a product of two polynomials? Can I write it? One can say yes and the other can say no. I got to give an answer for both the people. So now if I'm going to say x power 7, one can say why can't I write x power 7 minus 5x square plus 7 into 1x, something like that. So if I'm going to multiply, I should get back this one. So if I'm going to put x power 7 in one bracket, what will I use it in the other one? Even if I include the minimum x, that is 1 power of x, when I multiply, I'll be resulting in x power 8. Whereas x power 8 is not here. So 7 is a prime number which cannot be factorized. So if 7 has to be, if x power 7, I should write x power 7 into x power 1, then it will result in x power 8, which is highly impossible. That is why it is called as prime polynomials. So whenever you have prime numbers as your highest power, there is highly impossibility arises to separate them. So reducible polynomials are used in the process of dividing something. This is another beautiful application of reducible polynomials. I had told you where are the polynomials applied in my first lecture. I hope everyone remembers the picture what I used to describe the application of the polynomial. A roller coaster, right? Now reducible polynomials is wherever you find dividing something. For example, when you see a road divider, right, at the pavement, right, when people are walking at the side of the roads, you could see that there are stands and there are chains connected to it. I hope you remember. The chains will be connecting. So that will be a removable chain only. So when it is dividing, that particular thing is dividing. Likewise, it's a curve equation. So wherever you see division, dividing something, there comes the applications of reducible polynomials. So let's get into the next slide. So problem number 1 and 2 put up in one slide. So just very simple problems to start up with. We are going to test a polynomial, whether it is irreducible or not. That's it. So it is irreducible over Z, Q, R and C they have given. See the mention. They have mentioned the set of integers, sort of rational numbers, real numbers and complex numbers. So solution, f of x is equal to 2x square plus 4. Okay. So no need to worry about this. So what do? I'm going to equate this to be 0. So equating this to 0, I'll be getting x square is equal to minus 2. So I'm going to take plus 2 over the right hand side. It's going to be minus 2. So what is my value of x? X is equal to plus or minus I root 2. So here, what is the value? It is the imaginary values, imaginary roots I'm getting. So once if the imaginary roots, can I write it as a product of these two? Yes, of course I can write it as x plus I root 2 into x minus I root 2. Able to follow? So I can take up this 2x square plus 4 is equal to x plus I root 2 multiplied by x minus I root 2. So product of these two. So what are the roots? What kind of roots are they? To which, where does it belong? Whether to Z, Q, R or C? So it belongs to C. So since it's a complex number, since I is present. So clearly they have told that the roots do not belong to Z, Q and R. Therefore, the function is irreducible over Z, Q and R. Are you able to follow? They are irreducible over Z, Q and R. But it is reducible over C. Since we got a complex root. If this would have been a real root, I could say it is reducible over R and irreducible over C or whatever it is. Since I have arrived at a complex number, depending on that, I will give my discussion. So the second problem. The second problem is f of x is equal to x square plus 1 in z of x is irreducible over z. They are asking you a question whether this polynomial x square plus 2, a second degree polynomial in z of x, they haven't mentioned any modulo here. Maybe modulo 1, obviously, right? So it's irreducible over z. So first what will I do? Given f of x, x square plus 1 in z of x. Now x square plus 1 is equal to 0, and taking this to plus 1 to the other side, you are getting x square is equal to minus 1, x is equal to plus or minus I. Okay, so here again it's going to be complex root. So complex root does not belong in z. So therefore this cannot be written as a product of two numbers. So I cannot write x square plus 1 is equal to x plus I into x minus I. You might ask me, we can write it. Yes, you can write it under C, but not over Z. That is why clearly they have told over Z. Since they have mentioned clearly over Z, we got to restrict by saying that it does not belong to Z and it is irreducible over Z. I hope you followed what is irreducible polynomial and how do you find irreducible and reducibility checking. We move on to problem number 3. So problem number 3, now we are coming at a modernization. So test the polynomial x square plus x plus 4 in z11 of x is irreducible over z11. So solution. So first I will declare what is given to me, and how will I write z11? This I have already told you. Starting from 0 and ending up at 10 as a field. Since 11 is a prime number, right? Okay. No issues in that. So what we start whenever we have a modulo, as I told you, even for finding the roots. So we start taking each number from that particular modulo set and start substituting inside the function and see what is a remainder for that. So let's start with the first number. The first number is 0. So if I'm going to put substitute 0, what will happen to the function? 0, 0 and 4. I'm getting an answer 4. 4 is a number which is less than 11. So, which is not equal to 0. So, no need to mention like this. You just put not equal to 0 under modulo 11. Both have the carrying the same meaning. Or else, if you want to put it in negative, what will be the negative number? 4 is how much short of 11? Can you tell me? It is going to be 7 short of 11. So, this can also be written as congruent to minus 7 mod 11. That can also be done. Okay, or else you can just leave it off. So now we move on to 1, the second number. So take the second number, substitute it in this function, you get the answer as 6. 6 is less than 11. So either you can write it as not equal to 0, or you can write how much short of 11. So it's going to be minus 5 short of 11. So writing minus 5. Second number 2. Substitute 2, I'm getting 10. So 10 is minus 1 short of 11. So which is not equal to 0. And F3, 16. So again, it's 5 short of 11, which is not equal to 0. F of 4, 4 square plus 4, you get 24. 24 means 22 and remainder is 2. So which is again not equal to 0. And F of 5 is equal to 5 square plus 5 plus 4 is equal to 34, which is congruent to 34 in the sense 33, and the remainder will be 1. So which is not equal to 0 again. So again we move on to F6. F6 will be, the answer is 46, right? So till 44 we have, we can write it for 11 and the remainder is 2 over here, and this is also not equal to 0. Till now, out of 11 integers, we have seen that from 0 to 6, 7 integers are not getting the remainder 0. So let's check, let's see for 7, 8, 9 and 10 in the next slide. So now f of 7 is equal to, when I substitute, we'll be getting 60. 49 plus 7 plus 4, 60. So is 60 divisible by 11? No. So what is the short of 60? Not short of, sorry. So it is going to be 55. The closer number is 55 and the remainder is 5, which is not equal to 0. And f of 8, the answer is 76. Okay. The closer number will be 66 and the remainder is 10, which is not equal to 0. F of 9, the answer is 94, which is congruent to 6. That is a remainder what you're getting as 6. Why? Because 88. 88 is the closest number and the remainder is 6, which is not equal to 0. And finally coming to f of 10. The number is 114. So the remainder is 4 here. So 11 tens are 110. The remainder is 4. So this is also not equal to 0. So starting from the element 0 and ending till 10, all the numbers, all the integers when substituted, it is not yielding a remainder 0. So therefore there is no root in Z11. So therefore f of x is irreducible over 11. Is that clear? So you might ask me straight away, when looking at this 11, I say it's irreducible. Okay, so I can, but it depends upon the polynomials, right? Depend upon the polynomial functions. For every polynomial, we cannot declare it. At times, see, for example, here, it is very much closer to 66. So suppose if I get 66, there will be a remainder. So the remainder will be 0 at times. So depends upon the polynomial. So don't come to a conclusion by looking at whether it's prime or that. If it is mentioned under modulo, definitely you have to perform all these steps, because modulo division cannot be taken things for granted. Okay, we move on to the next slide. Okay, before getting on to the end of the PPT, recap of what is a reducible polynomial, what is irreducible polynomial. So a polynomial which can be splitted as a product of two polynomials. So try to understand, a polynomial which can be splitted as product of two polynomials, then we can call that polynomial as a reducible polynomial. If I cannot split that particular polynomial as a product of two polynomials, then I can call that as a irreducible polynomials. Is that clear? So irreducible polynomials, moreover, for a very simple problem, for a 2 marks questions, etc., if you could see that it is a prime number, prime power, it is very highly uncomfortable for us to split that as a two products. So suppose if a question comes, write any two irreducible polynomials. So what should be your answer? You should choose the polynomial, the highest degree of the polynomial as a prime number, so that it cannot be factored. For example, if they're going to ask the same question vice versa, then you should understand the term that you can take up any even number, even higher degree power polynomial. For example, x power 4 or something like that, x power 4, 6, something like that. If x power 6, how can I split it up? X power 3 into x power 2 or whatever it may be. So likewise you can split it up so that you can get your polynomials. So thanks for watching the video, and hope you understood the irreducible and reducible polynomials. So I'll catch you up in my next lecture. Thank you so much. Please revise the practice questions which are put up in the Google Meet. Thank you so much.